are you doing?
Hi, this is Mr. Heebner, and we are working today on a specific heat lab, specifically heat of fusion. So we're going to be looking at water and ice, and we're going to be doing an experiment to determine the heat of fusion of ice. It's 334 joules per gram. But before we do that, we got some background information we need to get going with. We got specific heat. Specific heat. What is specific heat? It is the amount of energy required. Yep, I would be writing this down. So amount of energy required to... Yeah, that's all right. One gram of a substance, 1 degree Celsius. That is specific heat. Amount of energy required to raise 1 gram of substance, 1 degree Celsius.
So, is this just like paper?
That's no paper, yeah, it's scrap paper.
Okay, so this is
That's nothing, yeah.
To raise 1 gram of substances, so that's a...
Yep, 1 gram of a substance, 1 degree Celsius. Alright. So, every single substance has its own unique specific heat. Water has a very high specific heat. And for example, if you are, it's July, it's a really hot day out, you're wearing short shorts, and there's a metal chair, and there's a wood chair, which one's going to be really hot? The metal one, you got it. Because the metal chair has a very low specific heat, so the temperature increases very quickly. Whereas the wood chair is a low specific heat.
what guy
There you go. Yeah, so if you're
wears... water?
typical guy, then you can sit in the chair and be fine. Alright, then we got heat,
Does this say substance?
substance. Heat of fusion.
Is there a Zoom right now?
No, nobody's on Zoom, but yeah, we are recording.
Well, Josh Radin's asked if there's
No, he doesn't do that. He's good. But there is a virtual lab to be running.
Oh, I live like 3 minutes.
So comparing the specific heat thing to something real life, you got Lake Michigan. Jaden, Lake Michigan's got a lot of water in it. It's a high specific heat. What do we know about Milwaukee's temperature right now compared to
It's colder than here because it's by the lake.
Close. It's warmer over in Milwaukee because it's by the lake. So,
Wait, what? Wait, no, it's definitely... Oh, in the summer it's colder.
in the summer, it's colder in Milwaukee. It's cooler. So why is that? Because it's warmer because you got the lake that has all of this energy in it in the summer and it's dissipating out. So when you're close to the lake, it's warmer in the winter. But then in the summertime, it's absorbing all of this energy. So it makes it cooler all night. But, if the Earth froze over permanently, eventually it'd be just as cold on the lake.
So it's
As in-
all
Yep, so because it has a high specific heat over the summer, it absorbs all this energy. So because our planet is 3/4 water on the surface, water's high specific heat has a huge impact on climates, making it a very stable planet to live on because you don't have drastic temperature changes with all the water. All right, heat of fusion, amount of energy required. Amount of energy required to melt 1 gram of a substance. So this is what we're going to be experimentally determining today, heat of fusion of water. How much energy does it take to melt 1 gram of a substance? And every single substance has a unique heat of fusion. Let's just write a quick little heating cooling diagram. We got solid, liquid, gas. As you increase energy, you're going to be increasing the temperature. So solids, as you heat it up, it's going to increase in temperature. But then what happens between solid and liquid? It has to do what?
Change.
It has to change via melting. But when something is melting and you take the temperature of it, it's not going to increase. It's going to stay the same. Until it's all melted, all liquid, then the temperature will rise. Until it starts to turn to a gas, then the temperature will not rise. Until it's all a gas, then it rises. Well, yeah, then there's plasma, but then plasma is broken up. Oh, so we got solid, liquid, gas, and then this says melt. All right, we're going to do an example. Melt. Yep. So in this example, we got 450 grams of water. We're going to cool it from 25 to 4 degrees Celsius. And the specific heat of water is always 4.184. And what we're going to try to do is find how much energy is released or absorbed. So we got to use the Q equals mc delta T equation. Alright, and Q is energy. M is mass. C is specific heat. And delta T is change in temperature. Q equals mc delta T. So we got that equation, we got all of our data. Our mass is 450. Where? There. Oh, MC delta T, triangle.
Oh, the triangle?
Yeah.
What's the energy?
Oh yeah, that's a Q. That's not correct.
Oh.
No. Yeah, like that place. I don't know. Maybe I'm doing cursive wrong. Wait. Oh my gosh, I need to work on the cursive. I can spell my name. You could write it like, how does a manuscript Q? Is that a manuscript Q? Yeah. Okay, yeah, you could write a manuscript Q. If you wanted to, but yeah, technically it's going to be Q equals. Oh. Alright, so Q equals 450. Specific heat is 4.184. And our change in temperature is final minus initial, 4 minus 25. That's a J. Joules, which is the unit for energy.
I don't understand.
So, normally we would spend a lot more time on this. We're just getting exposed to the concepts just because of our goofy schedule. Alright, so 4 minus 25. Cole, what's 4 minus 25?
What?
What's 4 minus 25?
Something negative.
It's something negative 21. There it is, yeah. 21 negative times 4.184 times 450. What's up?
Hi.
I think it is.
What?
Actually, it might not be. That's very controversial. Is the absence of something something? Alright, so negative 39,538.9, actually 0.8. Well, we're gonna get to the fun part pretty soon. So
53.8.
Yep, 538.8. So that's how much energy is released. So this is an exothermic process because energy is negative. It's released.
Sorry.
All right. Doing another question. This is the last one. Then we're going to get to the really fun part. All right. This is the Saturday morning group. All right. 100 grams. So heat of fusion is given to you. We got 300. We're almost done. 334 joules per gram. That's the amount of energy needed to melt 1 gram of water. 334. That's going to be the magic number that you're going to try to get to in the experiment. Let's say in this example, we got 100 grams. The equation is Q equals mass times heat of fusion. Mass times heat of fusion. There it is. All right. That's a J. Yep. So Q equals 100 times 334.
Is that an S?
FUS.
It's between the M and H.
That's a triangle.
Oh, I thought it was a cursive S for a second.
No, triangle.
How much of this unit is going to be on the final exam?
0 this year.
Well, we have another exam.
So, the final exam, yeah. Yeah, that's the only assessment that's left. So. All right, and that is that. We're going to get onto the lab in a little bit.
Yo, homies, guess what? It's the Hair Bear at it again. I'm back! Woo! Alright. So today, we're doing a really sick experiment called water boiling. Woo! It's some pretty cool stuff, I can't lie. So, in essence, what we're doing today is we're boiling this here water, okay? Or not boiling, but we're heating it up quite a bit so that it's at 50 degrees Celsius. And then, because we gotta add a twist, okay, we're getting the volume and mass of this after it's been heated up. And then, we're putting it in a styrofoam cup. Woo, that's not suspicious at all. Alright, and after we're done with that, we put ice into it, and we're calculating the volume and temperature of it until it hits 0 degrees Celsius. Okay, the goal is 0 degrees, but we might just get it to like 3 because that's not in the curriculum today. Woo! Alright. I believe that there's a Mr. Hebner video showing the calculations of the whole thing, so adios, homies, it's been the Hair Bear! How do I turn it off? It won't turn off. Hi guys, we're just doing some primo time here. Yeah, this is some real cool stuff we're doing, isn't it, guys?
All right, so calculations. Using the known density of water, find the mass of the original volume of water. All right, so this is questions on calculations. We got M1 and V1. So, all right, sorry for that background noise there. All right, what we got going on is the density of water is 1 gram per milliliter. That means if you got 1 gram, you got 1 milliliter. If you got 100 milliliters, you got 100 grams. So, let's use your data. What was the volume that you had for your volume 1? 100. There you go. So how many grams do you have? You got 100 grams. Find the mass of M1. All right, so our mass of M1 is 100 grams because our volume 1 was 100. All right, find the volume of water due to the melted ice. So basically, we take our final volume after the ice melted minus the original volume before you added ice. What did you guys get when you subtracted them? Or what was your final volume? 150. All right. And your original volume was 100. All right, so 50. Oh wait, let me post this on here. All right, and then find the mass of this volume of water. All right, well, the density of water is 1 gram per milliliter. Then it would be 50 grams. All right. And then find the change in temperature of the water. What was your final temperature?
5 degrees.
5 degrees. And your starting was what? 50. All right. So that's negative 45 degrees Celsius. I don't have time to put the little degree sign, but all right. And then find the heat lost by the original mass of water. Okay, so delta Q equals mc delta T. So our mass 1 was 100. All right. Our change in temperature was negative 45. And our specific heat of water is always 4.184. This joules per gram degree Celsius. All right. So I'm going to have to take a calculator and multiply this out. 100 times 4.184 times 45, and it's negative. And I'm getting 18,828. Negative 18,828, and that's joules. All right, so that's the amount of energy that's being released into basically the ice. Actually, no, it's 100 grams. It's the amount of energy that's being released from the water. There you go. All right, so then we got to find the heat of fusion of ice. So that's our change in Q, the negative 18,828, divided by our change in mass, which was 50. All right, so negative 18,828 divided by 50 negative 376.5. All right, so that's not bad actually, because if you remember from our example in the beginning of class, 334 is our accepted value. Oh, it says it right there. There it is. Find your percent air. The actual value of the heat of fusion of ice is 334 joules per gram. There's no temperature in there. Let's get that out of there. Okay, percent air, remember, is accepted minus experiment divided by accepted. So our accepted is 334. Our experiment is 376. And so I put a negative here. Let's see, that just means it's melting. If it's positive, it means it's freezing. So I'm just going to take positive values of both of them. Divided by 334, and then you times the whole thing by 100. All right, so 334 minus 376.56 divided by 334 times 100. It's an absolute value, so it's always positive. I'm getting 12.7%. Not bad. Not the best data that's been found, but it's not bad. 12.7. There we go. Okay, so list 2 possible sources of error. So why didn't we get 0% error? There's some possibilities. Some aren't your fault, some might be. Okay, it didn't go down to 0. Look at that. So some of these thermometers aren't the greatest. 0 degree Celsius. And then, I don't know, maybe we need to put more ice and wait a little bit longer. Some possibilities, but it didn't go down to 0, so that's going to be a factor. What's another possible error? What was it?
You can start with the right amount of water. Like you didn't have exactly 100.
Okay, yeah, maybe you're off a little bit, you know. Measurement off slightly. Maybe just kind of rounded it. Styrofoam cup, is energy going to come out of that styrofoam cup? Well, yeah. So it's just not as much as like a metal cup. So that could be another one, just a cup that we used. It would, yeah. The temperature would go up and down a lot quicker. Define the following terms: exothermic, endothermic, heat diffusion, specific heat. Let's see. Okay, so all right, that's pretty much that pertains to the lab. The rest is just kind of extra concepts behind it. But exothermic means energy is released. Endothermic means energy is absorbed. Heat of fusion, remember, is the amount of energy required to melt a gram of a substance. And the specific heat capacity is the amount of energy required to raise 1 gram of a substance 1 degree Celsius. So those two are right from your notes in the beginning. And then, is the process of melting exothermic or endothermic? So when something is melting, is it getting warmer, kind of? Or, it actually doesn't get warmer until it's all melted. But like when something is melting, usually you have heat going into it, right? So that would be, it would actually be an endothermic process. When something's melting, it's receiving heat, so it's endothermic. If something's freezing, it's throwing off heat and getting colder, so that's an exothermic process. Which is kind of weird because exothermic you think is hot, endo you think is cold, so it's kind of counterintuitive. All right, I'm going to stop that video. So nice job, and if you got any questions, you can email me and all that stuff. All right.